You've partitioned your data across 10 nodes. A client wants to read key 48291. Which node holds it? How does the client find out? This is the request routing problem, and it's more subtle than it first appears. The challenge is that partition assignments change. Rebalancing moves partitions between nodes. Any component that knows the routing table must be updated when partitions move. And partition assignments can change while requests are in flight. The book identifies 3 architectures for solving this. The first is to let clients contact any node directly. If that node holds the requested partition, it handles the request. If not, it forwards the request to the correct node, receives the response, and relays it back to the client. Every node knows the complete partition map and can act as a router for any key. The second is a dedicated routing tier, a component that sits between clients and nodes, knows the current partition assignment, and routes each request to the right node. Clients talk to the routing tier, which has no data but has full knowledge of the partition map. This is the role played by Mongo's router process. The third is smart clients. The client itself knows the partition assignment and connects directly to the appropriate node without any intermediary. This requires the client library to track the partition map and update it when partitions are rebalanced. All 3 architectures have the same underlying requirement: something must track partition assignments and be updated when they change. That component becomes a consistency problem in its own right. The most widely adopted solution for tracking partition assignments is to use a separate coordination service, a system specifically designed to store small amounts of configuration data that must be consistent and available. ZooKeeper is the dominant choice. It's used by HBase, SolarCloud, Kafka, and LinkedIn's Helix to track which partitions belong to which nodes. When a rebalance occurs, the database updates ZooKeeper. Other components, routing tiers, client libraries, monitoring systems subscribe to ZooKeeper for change notifications. When ZooKeeper signals a change, they update their local routing tables. ZooKeeper is designed for this use case. It provides strong consistency guarantees for a small key value store that many components can watch for changes. It's not a general-purpose database. It would be a terrible choice for storing application data. But for partition 42 is currently on node 7, was on node 3 before the rebalance at 14 hours 32 minutes and 7 seconds, it excels. Cassandra and Ryak take a different approach that eliminates the need for a separate coordination service entirely, the gossip protocol. Instead of a central authority, each node periodically contacts a few random other nodes and they exchange their knowledge of the cluster state. A change on one node, a new partition assignment, a node joining or leaving, propagates throughout the cluster over successive gossip rounds. Gossip is eventually consistent. Not all nodes know about a change at the same moment. But for partition routing, this is acceptable. A client that routes to a slightly stale partition assignment will get forwarded by the node, or will retry when it discovers the assignment has changed. The gossip protocol eliminates the single coordination service as a potential bottleneck or failure point, at the cost of some routing table staleness during transitions. This is the book's final observation about partitioning. Partition assignment tracking is a distributed systems problem in its own right. The routing layer must handle stale information gracefully, because no matter how it's implemented, there will always be moments when different parts of the system have different views of where data lives.